Long before humans roamed the oceans, colossal predators ruled the seas. Among them, the Megalodon is often remembered as the ultimate shark, a titanic, tooth-lined predator capable of crushing whales with ease. Yet, beneath the waves of the prehistoric oceans, there existed sharks far deadlier, faster, and more strategically terrifying than the Megalodon. From razor-toothed hunters with streamlined bodies built for speed, to armored giants that dominated reef ecosystems, these apex predators shaped the evolution of marine life millions of years before our species appeared. In this series, we explore the sharks, science's only beginning to understand predators, whose power, adaptations, and hunting strategies surpassed even the legendary Megalodon in subtle and deadly ways. Cretolamna, the speed demon of the Cretaceous. The seas of the late Cretaceous were alive with motion, a mosaic of colour and chaos where survival depended on speed, awareness, and precision. Amid the swirling schools of fish and darting marine reptiles, Cretolamna patrolled the midwater like a shadow of motion, small by prehistoric standards, yet perfectly designed to dominate its niche. Fossil teeth discovered across continents reveal not just size, but the story of a predator honed for slicing, tearing, and hunting with unmatched efficiency. Unlike the lumbering giants that would come later, Cretolamna relied on bursts of incredible speed to strike. Its fusiform body minimized drag, while the stiff, crescent-shaped tail acted like a turbocharged propeller. Vertebral fossils suggest a spine capable of agile undulation, allowing sudden turns and directional changes that would have left prey disoriented in a split second. This was a shark built for surprise, a predator that didn't rely on sheer power, but on calculated, instantaneous motion. Its teeth tell a story of specialization. Serrated and recurved, they were perfectly adapted for cutting through the soft flesh of fast-moving fish or small cephalopods. Unlike Megalodon, which crushed bones, Cretolamna struck with precision, targeting mobility and efficiency. The slight variations in tooth curvature across fossil specimens hint at evolutionary experimentation. Some individuals may have specialized in schooling fish, while others targeted smaller marine reptiles. But speed and teeth alone do not define a hunter. Cretolamna's sensory systems were just as refined as its skeleton. Its eyes, forward positioned for depth perception, combined with electroreceptors along its snout and a finely tuned lateral line, gave it a 360-degree awareness of the surrounding water. In murky seas, it could detect the heartbeat of a distant fish or the subtle vibration of a fleeing cephalopod, allowing it to strike with astonishing accuracy before prey could react. Cretolamna's ecological role extended far beyond individual kills. By hunting agile fish and small marine reptiles, it forced entire species to adapt in speed, schooling, behavior, and evasive maneuvers. Its presence shaped the evolutionary pressures of the midwater column, influencing predator-prey dynamics long before Megalodon would reign supreme. In this way, it was both hunter and unseen architect, shaping the behavior and distribution of the creatures it hunted. Flexibility defined Cretolamna. Its mid-sized frame allowed it to hunt in both open water and near reefs, exploiting niches that larger, slower predators could not. Fossils indicate a global distribution, suggesting it was capable of adapting to a variety of marine environments, from shallow coastal waters to deeper oceanic zones. Evolution favored a combination of speed, precision, and adaptability traits that allowed Cretolamna to thrive in a world filled with competitors. Perhaps most fascinating is how Cretolamna redefined lethality without relying on size. While the Megalodon would eventually dominate imagination and oceans alike, Cretolamna's mastery lay in the subtlety of its strikes, the efficiency of its sensory systems, and the calculated timing of its attacks. Fossils preserve a predator that exemplifies evolutionary ingenuity, proving that in the oceans of the Cretaceous, finesse could outweigh brute strength. Cretolamna reminds us that being deadly is more than raw power. It is strategy, agility, and a keen understanding of the environment. Every undulating movement, every precise strike, every calculated bite reveals an apex predator perfectly adapted for its ecosystem. In the chaotic currents and predator-rich waters of the late Cretaceous, Cretolamna reigned as a shadow of lethal grace, a predator whose story is preserved not only in teeth and bones, but in the ripple effects it left on the ocean itself. Otodus oblioquus, the giant ambush predator. Beneath the early Cenozoic waves, a predator of astonishing size moved with a terrifying combination of strength and precision. Otodus obliquus stretched up to 12 meters, a giant whose presence dominated the Paleocene and Eocene seas. Its teeth, massive yet finely serrated, reveal a predator capable of taking on the largest marine vertebrates of its time. Fossil finds across North America, Europe, and Africa tell the story of a shark whose lethal efficiency reshaped the oceans long before Megalodon ever existed. Unlike smaller, agile hunters, Otodus relied on a mix of stealth and explosive bursts of speed. Its vertebral column shows remarkable flexibility, allowing lateral undulations that could propel it suddenly toward prey. Fossilized remains suggest it could strike from below or behind unsuspecting animals, ambushing with terrifying precision. In open water, the giant could accelerate with power, closing distances in seconds, a predator that combined size, strategy, and agility. Its teeth were engineered for devastation. Broad, serrated, and slightly recurved, they could pierce flesh and bone with ease. Bite marks found on fossilized marine reptiles and other sharks indicate repeated predation rather than scavenging. Unlike Megalodon's massive crushing teeth, Otodus's dentition emphasized repeated, precise strikes, allowing it to attack swiftly and efficiently. Variations in tooth size across fossils suggest subtle specialization. Some individuals likely hunted faster fish, while others targeted larger vertebrates. Yet teeth and power were only part of Otodus's arsenal. Its sensory systems were finely tuned for predation. Electroreceptors detected the faint electrical pulses of prey, while its eyes provided binocular vision for judging distance and timing attacks. The lateral line allowed it to perceive subtle water currents, tracking even distant prey. This multi-sensory network gave Otodus a tactical advantage, turning every ambush into a calculated strike rather than a blind lunge. Otodus was a keystone predator. Its presence influenced prey behavior, forcing schools of fish and marine reptiles to develop new evasion strategies. Smaller predators adapted to its hunting patterns, while the distribution of marine life itself was subtly shaped by its dominance. In essence, Otodus not only hunted but orchestrated a complex web of predator-prey dynamics that resonated through the oceans for millions of years. Flexibility and adaptability were crucial to its success. Fossil evidence indicates that Otodus inhabited both coastal and open ocean zones, exploiting prey across a wide range of habitats. Its massive size could intimidate competitors, yet its mobility allowed it to exploit environments where brute strength alone would be insufficient. This combination of versatility and power underscores the evolutionary sophistication that allowed Otodus to dominate early Cenozoic seas. Predation for Otodus was not simply a matter of force. The shark balanced stealth, timing, and repeated precision strikes to subdue prey effectively. Fossilized gut contents and bite marks show a varied diet, including fish, smaller sharks, and marine reptiles. Each hunting event required coordination, speed, and sensory awareness, a demonstration that lethality is as much about strategy as it is about raw size. Otodus obliquus offers a window into a prehistoric ocean ruled by evolutionary experimentation. Its combination of sensory refinement, anatomical power, and predatory intelligence allowed it to thrive in competitive waters. While Megalodon would later capture human imagination as the ultimate shark, Otodus demonstrates that apex predation relied on more than brute force. In these ancient seas, dominance was measured in the mastery of movement, perception, and lethal precision. Even today, the fossils of Otodus inspire awe. They capture the scale, strength, and sophistication of a shark that moved with grace and power across the prehistoric oceans. Its legacy persists not only in its own evolutionary lineage, but also in the imprint it left on the behavior, distribution, and survival strategies of countless marine species. Otodus reminds us that in the oceans of deep time, lethality was a complex interplay of size, intelligence, and environmental mastery, a predator perfectly adapted for its world. Cretoxyrhina, the ghost of the Cretaceous seas. In the open oceans of the late Cretaceous, a predator glided through the waters like a shadow, unseen until it struck with lethal precision. Cretoxyrhina, sometimes nicknamed the Ginsu shark by paleontologists for its blade-like teeth, reached lengths of up to 7 meters. Fossilized teeth and vertebrae found in North America and Europe reveal a predator optimized for speed, surprise, and efficiency, a shark that hunted with intelligence as much as power. Unlike larger, lumbering predators, Cretoxyrhina relied on bursts of velocity to ambush prey. Its streamlined, fusiform body minimized drag, while a crescent-shaped tail provided sudden thrusts capable of catching even the swiftest bony fish or juvenile mosasaurs. Vertebral fossils suggest remarkable spinal flexibility, allowing subtle maneuvers mid-strike, making it a predator that could adjust trajectory mid-attack with uncanny precision. Its teeth were a masterclass in evolutionary design. Broad at the base, sharply serrated along the edges, and slightly recurved, they could slice through flesh cleanly and repeatedly. Bite marks on fossilized fish, marine reptiles, and smaller sharks indicate that Cretoxyrhina attacked with rapid strikes, disabling prey efficiently without expending unnecessary energy. Unlike Megalodon, which crushed, Cretoxyrhina carved through its prey with speed and efficiency, a true artisan of predation. Sensory adaptation played a critical role in its hunting success. Electroreceptors along the snout could detect subtle electrical signals from prey hidden in murky water, while binocular vision allowed precise depth perception for accurate strikes. The lateral line system detected vibrations in the water, enabling it to sense even the slightest movement in schools of fish or among fleeing marine reptiles. This combination made Cretoxyrhina a hunter that saw the ocean not just as space, but as a web of energy, movement, and opportunity. Cretoxyrhina was a keystone predator. Its predation shaped the behavior of prey species and influenced other predators' strategies. Schools of fish developed evasive patterns, smaller sharks avoided certain hunting grounds, and juvenile marine reptiles relied on speed and camouflage for survival. Fossil evidence shows bite marks on other predators, suggesting that Cretoxyrhina occasionally competed with its own kind or attacked rivals a predator whose influence extended beyond its immediate kills. Flexibility in habitat allowed Cretoxyrhina to thrive across the late Cretaceous seas. Fossils indicate it could hunt both in nearshore waters and open oceans, exploiting niches unavailable to slower, larger sharks. Its body plan combined speed, power, and maneuverability, allowing it to chase prey, ambush unsuspecting animals, and adapt to a range of environmental pressures. This versatility made it one of the most successful predators of its era. Hunting behavior in Critoxorhina was an art of timing and coordination. It likely used a combination of stealth and acceleration, cruising the midwater column to identify prey before striking in sudden bursts of speed. Teeth could slice efficiently, while its flexible body allowed mid-attack adjustments. Fossil evidence of multiple bite marks on single prey items suggests repeated strikes, indicating patience and tactical thinking rather than brute force attacks. Critoxorhina demonstrates how predation in the Cretaceous favoured precision and sensory awareness as much as power. Its teeth, vertebral structure, and sensory systems show adaptations for exploiting multiple prey types, from fast-moving fish to small mosasaurs. These evolutionary refinements highlight a predator whose success relied on intelligence, versatility, and the ability to dominate through speed and strategy rather than sheer size. Through Critoxorhina, we glimpse the deadly elegance of Cretaceous apex predators. It reminds us that oceans were arenas of subtlety, where survival depended on timing, adaptation, and environmental mastery. While Megalodon captures the modern imagination, Critoxorhina reveals that lethality in prehistoric seas was a balance of intelligence, speed, and precision qualities that allowed it to haunt the waters long before the titans emerged. Paratodus benedeni, the oceanic phantom, across the vast oceans of the Miocene, a ghost glided through the deep, largely unseen, yet capable of terrorizing entire marine communities. Paratodus benedeni was an enigmatic shark, often called the pelagic phantom, due to its rare fossil record and elusive nature. Reaching lengths of 6 to 7 meters, its narrow, streamlined body was optimized for speed and endurance, a hunter built to roam the open ocean for weeks at a time, tracking schools of fish and the occasional smaller shark with a predator's patience. Unlike reef-dwelling predators, Paratodus thrived in the pelagic zone. Fossil evidence, primarily isolated teeth, hints at a species adapted for endurance swimming rather than explosive attacks. Its slender, elongated body minimized resistance, allowing it to cruise across oceanic expanses with efficiency. This adaptation made it a persistent hunter. It could follow prey across hundreds of kilometers, relying on stamina and strategy rather than raw force to dominate its environment. The teeth of Paratodus were unusually narrow and curved, resembling delicate surgical blades more than brute force weapons. They were perfectly designed for grasping slippery prey such as bony fish or soft-bodied cephalopods, unlike the serrated crushing teeth of Megalodon or Otodus. Paratodus's dentition emphasizes precision and specialization. Fossil analysis suggests that even small mistakes during a strike could result in a lost meal, underscoring the shark's reliance on skill and exact timing. Sensory adaptations were critical to Paratodus's survival in the vast, featureless midwater. Its electroreceptive system allowed detection of tiny electrical fields from prey over long distances. Paired with a sensitive lateral line, it could detect even faint pressure waves from schools of fish swimming far below. Eyes likely adapted for low-light conditions, enabling the shark to hunt at various depths throughout the day. This combination made it a predator as much attuned to subtle environmental signals as to visual cues, allowing it to operate in a vast three-dimensional hunting arena. Paratodus was more than a solitary hunter. Its presence shaped entire oceanic ecosystems. By preying on pelagic fish and smaller sharks, It influenced migration patterns, school formations, and predator-prey dynamics. Other sharks and marine predators had to adjust hunting times and strategies, creating a ripple effect through the trophic web. Its rare fossil record makes it challenging to study, but even fragmentary evidence suggests that Parotidus played a critical, often underestimated role as a mid to upper tier oceanic predator. Flexibility in hunting strategy defined this shark. Fossil teeth found in disparate locations suggest a wide geographic range, indicating the ability to track migratory prey across vast distances. Its hunting behavior was likely a combination of slow, methodical tracking and sudden, precise attacks when prey came within reach. Unlike coastal predators that relied on structural complexity like reefs, Parotidus dominated open waters where cunning, endurance, and precise strikes determined success. Despite its size and capabilities, Parotidus's rarity in the fossil record hints at its elusiveness. Its life strategy prioritized stealth and endurance, allowing it to survive in the shadows of the ocean where fewer fossils could be preserved. This scarcity underscores its unique ecological niche, a predator adapted to life far from shorelines, relying on patience, efficiency, and subtlety over raw power. Parotidus illustrates a different type of shark success. While Megalodon and Otodus relied on size and power, Parotidus thrived on endurance, strategy, and precision. Its adaptations represent a specialized evolutionary path optimized for pelagic hunting, highlighting the diverse solutions sharks developed to dominate different marine environments. Studying this oceanic phantom deepens our understanding of how sharks could evolve to exploit virtually every marine niche, from reefs to the open ocean. Parotidus benedeni reminds us that lethality is not always flashy or obvious. In the open waters of the Miocene, it moved like a shadow, hunting efficiently, shaping prey behavior, and surviving in one of the most competitive marine environments ever known. Its life underscores a crucial lesson. Evolution often favors patience, precision, and adaptation, proving that even in the oceans, the deadliest predators were not always the largest or most visible. Carcharocles, auriculatus, the ancient giant, in the seas of the Oligocene, an apex predator patrolled the oceans with a silent, terrifying authority. Carcharocles auriculatus, a giant predatory shark and ancestor of the legendary Megalodon, could reach lengths of over 10 meters, its serrated teeth perfectly adapted to slicing through flesh and bone. Fossils of its teeth, scattered across every oceanic continent, tell a story of a predator that combined raw power with evolutionary refinement, making it one of the deadliest hunters of its time. Unlike the stealthy, mid-water predators such as Parotidus, Carcharocles auriculatus relied on brute force complemented by precision. Its massive jaws could crush thick bones and deliver fatal bites to marine mammals and smaller sharks alike. Yet beneath its imposing size lay a design honed for efficiency. The shark's streamlined body, preserved through rare fossil impressions, indicates it could sustain high speeds while chasing prey across open waters, a combination of power and mobility that few contemporaries could match. The teeth of Carcharocles auriculatus reveal evolutionary mastery. Broad, triangular, and finely serrated, they were capable of slicing through even the toughest hides, leaving distinctive marks in fossilized bones. Paleontologists have found bite patterns on smaller whales and marine reptiles, indicating repeated, calculated attacks. Unlike Megalodon's legendary crushing bite, these teeth emphasize a combination of slicing and gripping, a strategy that allowed this ancient giant to feed efficiently while conserving energy for subsequent strikes. Sensory adaptation gave this predator an evolutionary edge. Like modern lamniform sharks, Carcharocles auriculatus likely possessed electroreception to detect hidden or camouflaged prey. Its eyes, large and forward-facing, provided depth perception crucial for midwater attacks. The lateral line system allowed it to sense subtle vibrations in the water, creating a three-dimensional awareness of prey movement, even in turbulent or murky conditions. This sensory suite made it a master hunter, able to strike precisely and efficiently long before prey had any chance of escape. Carcharocles auriculatus shaped entire marine communities. Its predation influenced whale migration patterns, fish schooling behaviors, and the hunting strategies of smaller sharks. Fossilized bite marks suggest that juvenile and smaller individuals had to adapt to its presence or face near certain death. By exerting selective pressure on prey species, Carcharocles auriculatus indirectly shaped the evolutionary trajectories of marine vertebrates, highlighting the profound impact of apex predators on ecosystem dynamics. Flexibility in hunting was key to its dominance. Fossil evidence indicates that it could hunt in coastal regions as well as open oceans, adapting strategy and speed to the environment. Its powerful body allowed bursts of speed to capture swift prey, while its jaws and teeth provided the lethal force to subdue animals larger than itself. This combination of adaptability, strength, and precision ensured that it maintained apex status in a world filled with competitors. Predatory behavior in Carcharocles auriculatus was a mixture of patience and aggression. It likely patrolled the water column methodically, using its keen senses to locate prey before striking in sudden, calculated bursts. Fossil evidence of repeated bite marks on single prey items indicates persistence and strategy rather than reckless attacks. Every movement, from the swish of its tail to the angle of its jaws, was adapted for maximum hunting efficiency. Carcharocles auriculatus represents a crucial link in the lineage leading to Megalodon. Its adaptations in teeth design, jaw mechanics, and body shape foreshadowed the emergence of later megasharks. Studying its fossils allows scientists to understand how apex predatory strategies evolved over millions of years, balancing size, force, speed, and sensory sophistication to maintain dominance in dynamic marine ecosystems. Carcharocles auriculatus reminds us that in prehistoric oceans, lethality was multifaceted. Its combination of power, precision, sensory acuity, and environmental awareness allowed it to dominate for millions of years. While Megalodon may later capture the imagination of humanity, Carcharocles auriculatus serves as a reminder that apex predation was a story of adaptation, skill, and evolutionary mastery long before the largest shark ever swam the seas. Through this ancient giant, we glimpse the raw, calculated intelligence of prehistoric oceans. Its teeth, muscles, and sensory systems illustrate the artistry of predation, revealing a creature perfectly adapted to hunt, dominate, and shape life around it. In the turbulent waters of the Oligocene, Carcharocles auriculatus swam as a predator both feared and influential, a testament to the power of evolution in crafting apex hunters that could master the seas without leaving a shadow of doubt. Carcharocles sokolovi, the forgotten predator. In the murky coastal waters of the late Miocene, Carcharocles sokolovi ruled as one of the ocean's most formidable predators, often overshadowed by its more famous relatives. Measuring up to 8 meters, this shark combined size, power, and jaw efficiency, yet fossils remain rare, leaving much of its story shrouded in mystery. Its teeth, large and serrated, indicate a diet of marine mammals and smaller sharks, revealing a predator designed for both tearing and grasping, a lethal combination in a world of constant competition. Unlike the pelagic hunters that roamed open oceans, Carcharocles sokolovi specialized in nearshore ambushes. Its body was powerful yet flexible, optimized for sudden lunges from hidden positions, striking unsuspecting prey with bursts of velocity. Vertebral fossils suggest an ability to pivot mid-attack, making it a master of surprise. This combination of stealth and strength allowed it to hunt effectively alongside, or in competition with, other large Miocene predators. The teeth of Carcharocles sokolovi were a marvel of evolutionary design. Broad at the base, serrated along the edges, and slightly curved, they could slice through muscle and crush bone alike. Bite marks on fossilized marine mammal remains suggest repeated strikes rather than opportunistic feeding, emphasizing a predator that relied on calculated efficiency over brute force alone. Unlike Megalodon, which dominated through sheer jaw size, C. sokolovi used precision and strategy to subdue prey, making it both versatile and deadly. Sensory adaptation played a key role in its success. Electroreceptors detected even subtle electrical signals from prey hiding beneath the sand, while forward-facing eyes provided depth perception critical for ambush attacks. The lateral line system allowed detection of movement over considerable distances, letting C. sokolovi anticipate the approach of prey or rival predators. In combination, these senses allowed the shark to operate in low visibility, shallow waters where smaller prey might otherwise escape unnoticed. Carcharocles sokolovi influenced both prey behavior and predator dynamics. Its predation on marine mammals and juvenile sharks forced adaptations in swimming speed, schooling behavior, and habitat selection. Competing predators adjusted their hunting strategies to avoid confrontation, creating a complex network of predator-prey interactions. Its presence highlights how even rare apex predators could shape entire coastal ecosystems, sculpting evolutionary pressures that echoed across marine communities. Flexibility defined this predator's success. Fossil evidence suggests it could inhabit both open bays and near-shore reef systems, exploiting multiple niches to survive. Its combination of speed, maneuverability, and brute strength allowed it to hunt efficiently in varied habitats, giving it an edge over predators that relied solely on size or ambush tactics. Carcharocles sokolovi thrived not just through dominance, but through adaptability, an evolutionary strategy that ensured survival in a dynamic environment. Despite its size and capabilities, this shark remains largely forgotten in popular imagination. Its rarity in the fossil record mirrors its stealthy lifestyle, highlighting an apex predator that operated in shadows, relying on strategy and sensory precision rather than spectacle. Studying C. Sokolovi gives scientists insight into Miocene marine ecosystems, revealing a predator that balanced intelligence, agility, and power to thrive in a competitive world. Carcharocles sokolovi reminds us that lethality is multifaceted. In prehistoric oceans, survival required more than size. It demanded sensory acuity, strategic thinking, and adaptability. This predator exemplifies how evolutionary pressures sculpted sharks to dominate diverse niches, proving that even lesser-known species could wield immense influence over the ecosystems they inhabited. Through Carcharocles sokolovi, we glimpse an apex predator that perfected the art of ambush in coastal waters, shaping prey behavior, competing with other predators, and thriving in a world where only the clever, fast, and adaptable survived. Its story underscores that, long before the Megalodon legend, the oceans were home to predators capable of shaping the evolutionary path of entire ecosystems. Hemipristyscera, the serrated predator. In the warm, shallow seas of the Miocene, a shark carved its niche with teeth like jagged knives. Hemipristyscera, the serrated predator, reached lengths of over 4 meters, smaller than the giants of its time, but no less formidable. Its teeth, broad at the base and finely serrated along the edges, allowed it to slice cleanly through fish, marine mammals, and even rival sharks. Fossilized bite marks reveal a predator that relied on precise, repeated strikes rather than brute force, a specialist in efficiency and control. Unlike pelagic hunters that roamed the open ocean, Hemipristyscera thrived in nearshore and estuarine environments. Its body was muscular yet flexible, built for bursts of speed through complex underwater terrain. Fossil evidence suggests it could pivot and twist mid-attack, making it a master of ambush within reefs, sandbars, and mangrove-lined shallows. Its hunting style balanced patience and precision, striking with lethal accuracy before prey had a chance to react. The teeth of Hemipristyscera were its signature. Each upper tooth was designed to tear, while lower teeth acted as a grip, creating a dual system optimized for catching and processing struggling prey. Scientists have observed evidence of regrowth and variation in teeth shape, suggesting adaptation to diet and hunting strategy. Unlike the crushing or slicing teeth of Megalodon or Otodus, these specialized teeth reflect an evolutionary focus on agility, speed, and repetitive effectiveness. Sensory adaptations elevated Hemipristyscera beyond a simple predator. Electroreceptors along its snout could detect subtle electrical signals from prey hiding in sediment or under rocks. Its lateral line system tracked movements across the water column, while its eyes provided depth perception for precise attacks in shallow, light variable waters. This suite of senses allowed it to dominate coastal ecosystems where visibility and maneuverability were key to survival. Hemipristyscera had a disproportionate impact despite its moderate size. Its predation patterns influenced fish schooling, marine mammal migration, and the hunting strategies of smaller sharks. Fossil bite marks indicate it occasionally competed with contemporaries for prey, shaping behavioral adaptations across multiple species. Its presence demonstrates that even medium-sized sharks could hold apex influence when hunting, skill, sensory sophistication, and ecological strategy were combined. Flexibility defined this predator's lifestyle. Fossil evidence indicates Hemipristyscera could exploit diverse habitats, from reef edges to estuarine channels. Its muscular tail provided bursts of acceleration, while a streamlined body enabled both pursuit and ambush. By occupying niches inaccessible to slower, larger sharks, it thrived in competitive ecosystems, demonstrating that versatility and specialization could coexist in a single apex predator. Predatory strategy for Hemipristyscera was an art of timing. Likely stalking prey slowly through the shallows, it could strike in sudden bursts, applying repeated slicing bites until prey was subdued. Fossil evidence suggests multiple strikes on a single prey item, indicating calculated effort and persistence rather than reckless attacks. Each maneuver, from tail propulsion to jaw angle, was adapted for efficiency and lethality, illustrating evolutionary mastery of coastal hunting. Hemipristyscera provides insight into how sharks adapted to dynamic, complex environments. Its serrated teeth, sensory acuity, and body design reveal a predator specialized for nearshore ambush, capable of influencing entire marine communities. Unlike the massive oceanic predators, this shark thrived in shallow waters where precision, agility, and environmental awareness dictated survival. Through Hemipristis sera, we witness a predator that mastered the art of coastal hunting. Its teeth, body, and senses combine to create lethal efficiency, influencing prey behavior and shaping the evolution of other species. In the shallow seas of the Miocene, this serrated predator reigned as a master of ambush, reminding us that apex predation comes in many forms, not just in size, but in strategy, skill, and environmental mastery. Isurus hastalis, the broad-toothed hunter. In the turbulent waters of the Miocene and Pliocene, a shark streaked through the ocean with remarkable speed and precision. Isurus hastalis, a close relative of the modern mako shark, measured over 5 meters in length and was built for both pursuit and predation. Its broad, flattened teeth reveal a predator capable of gripping and slicing swiftly through fast-moving prey, from large bony fish to cephalopods, highlighting a hunting strategy centered on agility and efficiency rather than brute force alone. Unlike the coastal ambushers of its time, Isurus hastalis dominated the open ocean. Its fusiform body minimized drag, while a powerful, crescent-shaped tail allowed bursts of acceleration rivaling modern makos. Vertebral fossils indicate a highly flexible spine capable of rapid directional changes mid-pursuit, enabling the shark to chase down schooling fish and escape detection from other large predators. Speed was its primary weapon, paired with surgical precision. The teeth of Isurus hastalis were uniquely adapted for open ocean predation. Broad and slightly flattened, they allowed the shark to grasp slippery prey and deliver repeated, clean strikes without losing grip. Unlike the serrated slicing teeth of Carcharocles or Hemipristis, these teeth favored retention and repeated capture of agile prey. Variation in tooth morphology across fossil specimens suggests a degree of specialization, likely linked to diet and hunting environment. Sensory adaptations were key to its hunting success. Large, forward-facing eyes provided accurate depth perception for high-speed chases, while electroreceptors along the snout allowed detection of the faintest electrical signals from prey in open water. The lateral line system tracked subtle pressure changes, enabling Isurus hastalis to anticipate movements of both prey and competitors over long distances. This sensory suite transformed the shark into a precise and relentless hunter of the pelagic zone. Ecologically, Isurus hastalis was an apex predator of midwater communities. Its predation shaped the behavior and distribution of schooling fish, cephalopods, and even smaller sharks. Fossil evidence of bite marks on bony fish and other marine vertebrates suggests repeated strikes, indicating a predator that influenced prey populations not just through direct consumption, but by forcing adaptive behavior and migration patterns. Flexibility in hunting strategy defined Isurus hastalis. Its high-speed bursts allowed it to capture agile prey, while a streamlined, muscular body enabled efficient long-distance swimming. Unlike slower, ambush predators, it could maintain sustained pursuit across open water, exploiting prey in ways that required both endurance and precision. This combination of adaptability, stamina, and sensory awareness secured its dominance in the competitive Miocene and Pliocene oceans. Hunting for Isurus hastalis was an exercise in timing and coordination. It likely combined slow cruising with sudden acceleration to close distances in seconds, applying multiple bites if necessary. Fossilized teeth marks indicate a predator capable of repeated, efficient strikes without exhausting energy reserves. Its body design, sensory acuity, and tooth morphology together reveal a predator optimized for open ocean hunting, combining speed, precision, and endurance. Evolutionarily, Isurus hastalis provides insight into the adaptation of lamniform sharks to open water niches. Its combination of powerful musculature, broad teeth, and sophisticated sensory systems shows how predators evolved not only for size or strength, but for efficiency, speed, and environmental mastery. It demonstrates the ways apex sharks dominated varied marine ecosystems long before the modern oceans took shape. Through Isurus hastalis, we glimpse the apex predation of open seas, a shark that ruled not by brute force, but by mastery of movement, perception, and timing. Its broad teeth, sleek body, and precise hunting tactics remind us that in prehistoric oceans, survival depended on strategy, skill, and adaptation qualities that made this predator one of the most efficient hunters of its era. Cosmopolitodus hastalis, the global hunter. Across the oceans of the Pliocene, a shark traversed vast distances, earning its reputation as Cosmopolitodus hastalis, the global hunter. Measuring up to 6 meters, this apex predator possessed teeth broad at the base with finely serrated edges, capable of tearing through thick muscle and soft bone alike. Fossils from every major ocean indicate its widespread presence. A predator perfectly adapted to hunt in diverse environments, from temperate coasts to the open pelagic zones. Unlike coastal ambushers, Cosmopolitodus relied on endurance and range. Its streamlined body minimized drag, while the crescent-shaped tail provided bursts of speed sufficient to overtake fast-swimming fish and cephalopods. Vertebral fossils suggest remarkable flexibility, allowing agile maneuvers during high-speed pursuits. This combination of stamina, speed, and flexibility made it a master of long-range predation, capable of hunting across thousands of kilometers with minimal energy loss. The teeth of Cosmopolitodus hastalis were evolutionary marvels. Broad, serrated, and slightly recurved, they could grip and slice efficiently, making repeated strikes possible without breaking or dulling prematurely. Bite marks on fossilized marine mammals and other sharks indicate strategic feeding, suggesting that it often attacked in a series of calculated strikes. This predation style contrasts sharply with Megalodon's sheer, crushing force, demonstrating an evolutionary emphasis on efficiency, precision, and versatility. Sensory adaptations allowed Cosmopolitodus to dominate the open ocean. Large, forward-facing eyes enabled precise depth perception at high speeds, while electroreceptors along the snout could detect the faint electrical signals of prey from significant distances. The lateral line system provided awareness of surrounding water currents, allowing the shark to detect approaching schools or avoid rival predators. These sensory tools transformed Cosmopolitodus into a predator capable of hunting across the vast, three-dimensional expanse of the open sea. Ecologically, its influence extended across entire marine ecosystems. Predation by Cosmopolitodus shaped the behavior of schooling fish, cephalopods, and even other sharks. Evidence of bite marks on juvenile sharks suggests competition among apex predators, indicating that it not only hunted efficiently, but also influenced the dynamics of predator-prey interactions. Its widespread distribution demonstrates how a single apex predator could impact global marine communities through both predation and ecological presence. Flexibility in hunting strategy was a key to its success. Fossil evidence suggests it could operate effectively in both shallow coastal regions and deep oceanic zones, adjusting its attacks to the environment and prey type. Unlike slower, ambush-based predators, Cosmopolitodus combined endurance, agility, and timing to capture fast-moving prey efficiently. Its body design allowed bursts of acceleration for sudden strikes, while maintaining the stamina needed for long-distance hunting. Predatory behavior in Cosmopolitodus was calculated and efficient, likely combining slow cruising with sudden accelerations. It could close distance and deliver multiple precise bites in succession. Fossil evidence shows repeated attacks on single prey items, indicating persistence and tactical intelligence rather than reckless strikes. This predator exemplified how lethal efficiency could rival brute force, allowing it to thrive in competitive marine ecosystems. Evolutionarily, Cosmopolitodus hastilis demonstrates how apex predators adapted to global niches. Its combination of endurance, sensory acuity, and tooth morphology shows the diversification of lamniform sharks in response to a variety of prey and habitats. By occupying both coastal and pelagic environments, it ensured survival across changing oceanic conditions, shaping predator-prey interactions on a worldwide scale. Through Cosmopolitodus hastilis, we glimpse the mastery of open ocean predation. Its teeth, speed, and sensory systems illustrate a predator evolved for endurance, precision, and adaptability. In the Pliocene seas, this shark reigned as a global hunter, demonstrating that apex predation depended as much on skill, timing, and environmental awareness as it did on size, proving the oceans of the past were home to predators both complex and formidable. Chlamydosalacus, the frilled hunter, in the dimly lit depths of the ancient oceans, a living fossil glided with eerie precision. Chlamydosalacus, known today as the frilled shark, has remained largely unchanged for millions of years. A relic of prehistoric seas, its elongated eel-like body and 6 frilled gill slits allowed it to navigate the deep ocean with a sinuous, undulating motion, giving it a hunting advantage in the darkness where stealth and flexibility were more important than speed. Unlike the open water predators, the frilled shark relied on ambush tactics. Fossil evidence and modern observations suggest it could coil its body to strike quickly, capturing prey with a sudden lunge. Its needle-like, recurved teeth formed multiple rows, perfect for ensnaring slippery fish, squid, and cephalopods. This combination of rapid strike and entangling bite allowed Chlamydosalacus to feed efficiently in low-light conditions where other predators might struggle. The teeth of Chlamydosalacus are evolutionary marvels, tiny, recurved, and numerous. They ensured prey could be captured and prevented from escaping even in the shark's narrow mouth. Fossilized remains indicate similar structures existed in ancient relatives, showing that this predatory strategy has persisted for over 80 million years. Unlike large, crushing-toothed predators, the frilled shark used a strategy emphasizing entrapment, precision, and repeated bites, making it a specialist of the deep-sea ecosystem. Sensory adaptations are key to its success in dark waters. Large ampullae of Lorenzini detect minute electrical signals from prey, while its lateral line picks up subtle water movements. Its elongated body allows for sudden bursts of movement despite appearing slow, making it a master of surprise. In the abyss, where visibility is limited and food scarce, such adaptations allowed Chlamydosalacus to dominate the niche of a stealthy, low-light predator. The frilled shark has long influenced deep-sea communities. By preying on mid-sized fish and cephalopods, it shaped the behavior, distribution, and population dynamics of its prey. Fossil evidence suggests ancient Chlamydosalacus likely occupied similar roles, acting as a stealthy apex predator of deep-water habitats. Its rarity in the fossil record mirrors its elusive lifestyle, emphasizing the challenges of survival in dark, resource-limited environments. Flexibility in hunting is evident in its sinuous body and coil and strike approach. Unlike faster, open-water hunters, Chlamydosalacus could anchor its body and lunge at prey from concealed positions. Its morphology allows a mix of ambush and sustained stalking, giving it the ability to exploit resources that might be unavailable to other predators in the same habitat. Evolution favored subtlety and efficiency over brute force, a strategy that has persisted for millions of years. Predatory behavior in Chlamydosalicus demonstrates patience and precision. It likely used its serpentine body to follow prey silently before striking with multiple hooking teeth. Repeated biting allowed it to capture agile cephalopods and fish, a stark contrast to the one-bite kill strategies of larger lamniform sharks. Fossil teeth and vertebrae show that this method has remained largely unchanged, making it a testament to the effectiveness of evolutionary design. Chlamydosalicus represents a lineage that has survived mass extinctions and environmental shifts through specialization. Its body plan, hunting strategy, and sensory adaptations reveal a predator honed for deep water environments, maintaining apex efficiency without competing in the more visible, predator-rich shallow waters. Studying this shark provides insight into how predatory specialization can ensure survival across vast geological timescales. Through Chlamydosalicus, we glimpse a predator that has mastered deep-sea hunting. Its frilled gills, serpentine movements, and needle-like teeth make it an apex predator of dark waters, a living window into the oceans of the past. In both ancient and modern seas, it exemplifies that evolutionary mastery relies not just on size, but on precision, adaptability, and the ability to exploit niches others cannot, proving that, even in obscurity, lethal predators can dominate their environment. Striatolamia macrota, the coastal predator. Along the shallow coastal waters of the Miocene, Striatolamia macrota patrolled with relentless efficiency. Measuring up to 4 meters, this shark was smaller than the giants of its era, yet perfectly adapted to dominate nearshore ecosystems. Its slender, streamlined body allowed for quick bursts of speed, ideal for pursuing fast-moving fish and small marine mammals. Fossil teeth reveal an evolutionary design emphasizing gripping and slicing, optimized for repeated strikes rather than sheer crushing power. Unlike pelagic hunters, Striatolamia relied on agility and precision in complex environments such as estuaries, reefs, and river mouths. Its vertebral column suggests a flexible spine capable of rapid turns and twists, allowing it to navigate tight spaces where prey might seek refuge. This coastal specialization meant it could exploit niches inaccessible to larger, slower predators, becoming a master of nearshore hunting. The teeth of Striatolamia macrota were slender and pointed, slightly recurved, ideal for gripping slippery prey. Fossil evidence indicates these teeth frequently show signs of wear, suggesting repeated biting events during hunting. Unlike the broad, serrated teeth of Otodus or Carcharocles, these teeth highlight specialization for smaller, agile prey, reflecting an evolutionary path focused on speed, precision, and adaptability rather than brute force. Sensory adaptations made Striatolamia an effective hunter in shallow waters. Electroreceptors along its snout detected subtle electrical signals from prey hidden in sediment or under rocks, while its lateral line system picked up vibrations in the water caused by swimming schools of fish. Its forward-facing eyes provided depth perception, crucial for ambushes where timing and angle could make the difference between success and failure. Striatolamia macrota influenced nearshore marine communities. Its predation forced schools of fish to develop tighter formations, while smaller predators adjusted hunting behavior to avoid direct competition. Bite marks on fossilized marine mammals indicate repeated predation events, suggesting that this shark could significantly shape local population dynamics despite its moderate size. Its presence underscores how mid-sized predators can exert outsized influence in complex ecosystems. Flexibility defined its lifestyle. Fossil distribution shows Striatolamia inhabited both coastal and estuarine environments, capable of adapting to seasonal and geographic variations in prey availability. Its muscular tail provided bursts of acceleration for sudden attacks, while a streamlined body enabled efficient long-distance swimming along coastlines. This combination of endurance, agility, and tactical intelligence ensured dominance in a competitive nearshore environment. Hunting strategy for Striatolamia was a blend of patience and rapid precision. Likely stalking prey slowly through the shallows, it could execute sudden lunges with multiple biting sequences. Fossil teeth patterns indicate repeated strikes to subdue prey efficiently, emphasizing strategic efficiency over reckless attacks. This predator exemplified the evolutionary advantage of specialization in a habitat where maneuverability and stealth mattered more than size. Striatolamia macrota demonstrates the diversity of shark adaptations in the Miocene. Its slender body, pointed teeth, and sensory acuity allowed it to thrive alongside larger predators, exploiting coastal niches that favored speed and precision. It provides insight into how mid-sized predators maintained apex influence within specific habitats, proving that ecological success does not always require dominance in size alone. Through Striatolamia macrota, we glimpse a predator that perfected coastal hunting. Its teeth, body design, and sensory capabilities created a shark capable of dominating complex nearshore ecosystems. In the Miocene seas, it exemplified how evolutionary specialization and agility could rival brute force, proving that even relatively small sharks could leave an indelible mark on marine ecosystems. Galiocerdo aduncus, the Miocene tiger shark. In the bustling coastal waters of the Miocene, a predator patrolled with relentless appetite and unerring efficiency. Galiocerdo aduncus, an early relative of the modern tiger shark, reached lengths of 6 meters and possessed the jagged, serrated teeth characteristic of its lineage. Fossil evidence shows it preyed on fish, turtles, smaller sharks, and marine mammals, employing a hunting strategy defined by power, versatility, and opportunistic intelligence. Unlike more specialized predators, Galiocerdo aduncus thrived on variety. Its teeth, designed for cutting as well as crushing, allowed it to handle a wide range of prey types. Fossilized jaws reveal a combination of broad, serrated upper teeth for slicing and narrower lower teeth for gripping, a dual system perfectly suited for a predator that hunted anything it could overpower. This versatility gave it a competitive edge in the densely populated Miocene coastal ecosystems. The body of Galiocerdo aduncus was muscular yet agile. Its fusiform shape reduced drag, while a crescent-shaped tail fin provided bursts of acceleration necessary for chasing fast prey. Vertebral analysis suggests it could pivot and twist with precision, enabling ambush attacks among reefs, sandbars, and estuarine channels. Unlike large pelagic hunters, it could navigate complex nearshore habitats with ease, exploiting prey in areas inaccessible to slower, larger sharks. Sensory adaptations enhanced its predatory efficiency. Electroreceptors detected minute electrical signals from prey hiding under sand or vegetation, while its lateral line system sensed vibrations across the water column. Forward-facing eyes gave depth perception for precise attacks, particularly in murky or low-light conditions. This sensory sophistication allowed Galeocerdo to hunt effectively in diverse habitats, from shallow estuaries to reef fringes. Galeocerdo predation influenced the behavior and migration of prey species, forcing fish schools to adopt tighter formations and smaller predators to modify hunting patterns. Fossil evidence shows repeated bite marks on turtle shells and marine mammal bones, suggesting persistent hunting rather than opportunistic feeding. This predator's presence echoes the profound influence apex species can exert on coastal ecosystems. Flexibility defined its dominance. Galeocerdo could patrol shallow reefs, estuaries, and open bays, adapting its hunting tactics to prey type and environmental conditions. Its muscular tail and agile body allowed sudden lunges, rapid pursuits, and repeated strikes, while energy efficiency ensured it could maintain dominance across territories with high prey turnover. This combination of adaptability, power, and intelligence ensured survival in competitive Miocene waters. Predatory strategy for Galeocerdo combined patience, opportunism, and precision. Likely stalking prey with measured movements, it could execute sudden bursts of speed to strike multiple times in rapid succession. Bite marks on fossilized prey indicate repeated, precise strikes rather than single, crushing blows. This method maximized hunting efficiency while minimizing energy expenditure, demonstrating evolutionary mastery in nearshore predation. Galeocerdo provides a window into the rise of tiger sharks and their specialized predatory techniques. Its dentition, body structure, and sensory adaptations reflect an early design for versatile hunting in diverse coastal habitats. It illustrates how mid to large-sized predators maintained apex influence by combining power, agility, and opportunistic feeding strategies, offering insight into predator-prey dynamics in prehistoric ecosystems. Through Galeocerdo we witness the mastery of opportunistic coastal predation. Its teeth, muscular body, and sensory precision made it a versatile hunter, capable of dominating nearshore habitats and influencing prey behavior. In the Miocene seas, it exemplified how apex predators leveraged adaptability, intelligence, and brute force, proving that survival depended on more than size alone, a combination of versatility, strategy, and evolutionary refinement. Carcharhinus lucus, the prehistoric bull shark. In the warm, brackish waters of the Miocene, Carcharhinus lucus, an ancient relative of the modern bull shark, roamed estuaries, rivers, and shallow coastal seas with unrivaled adaptability. Measuring over 4 meters in length, this predator combined brute force with agility, thriving in environments where saltwater and freshwater converged. Its robust, conical teeth reveal a versatile predator capable of gripping struggling prey and delivering fatal bites, perfectly suited for hunting in variable aquatic habitats. Unlike specialized pelagic hunters, Carcharhinus lucus excelled in complex, confined environments. Its compact, muscular body allowed sudden bursts of speed, essential for navigating river channels, mangrove routes, and shallow reefs. Vertebral analysis indicates remarkable flexibility, enabling rapid turns and precise attacks in areas inaccessible to larger, slower sharks. This combination of strength and maneuverability made it the apex predator of transitional waters. The teeth of Carcharhinus lucus were designed for versatility. Broad, triangular, and slightly serrated, they could pierce tough hides and crush bones, while lower teeth held prey securely during repeated strikes. Fossil evidence shows bite marks on bony fish, turtles, and even smaller sharks, highlighting a predator that combined opportunistic feeding with calculated predatory efficiency. Unlike the specialized slicing teeth of Isurus or Hemipristis, these teeth reflect a generalist strategy optimized for diverse prey types. Sensory adaptations allowed this shark to dominate estuarine ecosystems. Electroreceptors detected faint electrical signals from prey hiding in sediment or murky water, while its lateral line system picked up subtle water movements. Forward-facing eyes provided depth perception, crucial for ambushes and rapid chases. Together, these adaptations allowed Carchahinus lucus to hunt successfully in habitats with low visibility and high complexity, where precision and speed were more important than sheer size. Ecologically, Carchahinus lucus shaped estuarine and coastal communities. Its predation influenced fish schooling patterns, turtle movements, and juvenile shark behaviors. Fossil evidence suggests repeated attacks on prey, implying strategic hunting rather than random opportunism. By dominating transitional habitats, it indirectly affected the distribution and survival of multiple species, demonstrating that apex influence could extend beyond direct predation. Flexibility defined its hunting approach. Fossil records indicate it could operate in freshwater rivers and marine bays, exploiting different prey populations depending on seasonal abundance. Its muscular tail and compact body enabled both rapid lunges and sustained pursuits, ensuring efficiency in hunting across a variety of aquatic conditions. This adaptability allowed Carcharinus lucus to survive and thrive where less versatile predators could not. Predatory strategy relied on patience, precision, and opportunism. It likely cruised slowly through channels or mangroves, using stealth to approach prey before delivering multiple, lethal strikes. Bite marks on fossilized fish and marine mammals indicate repeated targeting, demonstrating strategic efficiency over random attacks. Its hunting method highlights the evolutionary success of flexibility and opportunism in complex habitats. Evolutionarily, Carchahinus lucus represents a lineage finely tuned for transitional ecosystems. Its combination of muscular body, versatile teeth, and sensory sophistication illustrates how predators evolved to exploit environments bridging rivers and oceans. This species demonstrates that survival in prehistoric seas required more than brute strength. It demanded adaptability, intelligence, and the ability to dominate diverse ecological niches. Through Carchahinus lucus, we glimpse a predator that mastered the challenges of brackish and coastal environments. Its teeth, body, and sensory capabilities reveal an apex predator capable of versatility, precision, and influence. In Miocene waters, it reigned over transitional habitats, proving that evolutionary mastery often lies in flexibility, strategic hunting, and adaptation to variable, dynamic environments. Megahasma applegati, the ancient megamouth shark. In the dimly lit midwater zones of the Miocene, Megachasma applegati swam silently, a filter-feeding giant of the open ocean. Unlike the predatory giants dominating shallow coasts, this shark evolved to exploit an entirely different niche, consuming vast quantities of plankton and small nekton with its enormous, gaping mouth. Reaching lengths of up to 6 meters, its body was elongated and streamlined, allowing slow, energy-efficient cruising through nutrient-rich waters far from the shoreline. Unlike active hunters, Megachasma applegati relied on passive feeding strategies. Its massive, cavernous jaws, lined with tiny hooked teeth, acted as a strainer, capturing minute prey while allowing water to pass through. Fossilized jaws and teeth suggest adaptations for engulfing large volumes of water, reflecting a feeding strategy that prioritized energy efficiency over speed or predatory force. This unique lifestyle allowed it to thrive in open oceans with abundant plankton blooms. The teeth of Megachasma applegati, small and hook-shaped, were ill-suited for biting large prey, but perfect for holding tiny organisms caught during filter feeding. Fossil evidence shows that despite its size, this shark's mouth could efficiently trap small fish, crustaceans, and plankton in high-density feeding zones. Its dentition highlights an evolutionary departure from the slicing and crushing adaptations of lamniform and carcharocline sharks, emphasizing specialization in midwater grazing. Sensory adaptations were key to survival in deep or low-light environments. Electroreceptors along the snout allowed detection of dense prey swarms, while large eyes were likely adapted for low-light vision, enabling detection of subtle bioluminescent cues. The lateral line system helped sense water movements, assisting in positioning itself optimally within prey-rich currents. These adaptations ensured it could feed efficiently in mid-water, where visibility is low and prey is often patchy and unpredictable. Megachasma applegati occupied a niche unique among Miocene sharks. By consuming massive quantities of plankton, it influenced prey population dynamics and nutrient cycling in the midwater column. Its filter feeding behavior complemented the predatory dynamics of contemporaneous apex hunters, creating a complex and balanced marine ecosystem. Its existence demonstrates that dominance in the ocean does not always require predation. Specialized feeding strategies can be equally influential. Flexibility defined its cruising and feeding behavior. Fossil evidence suggests it inhabited multiple latitudes, likely following seasonal plankton blooms across vast distances. Its streamlined body, combined with low-energy swimming techniques, enabled it to exploit scattered food sources without expending unnecessary energy. This long-range adaptability made Megachasma applegati an efficient, enduring presence in open oceans. Hunting, or more accurately, feeding, relied on methodical, continuous swimming. The shark would open its cavernous mouth, drawing in both water and prey, using subtle head and jaw movements to maximize capture. Fossilized gill raker structures suggest repeated engulfing motions to trap as many organisms as possible, reflecting a feeding method perfectly adapted to a midwater filter feeding lifestyle. Unlike ambush predators, efficiency and persistence were the keys to its survival. Megachasma applegati reveals the diversity of shark strategies in prehistoric oceans. Its body form, dentition, and sensory adaptations illustrate how a lineage could survive not by predation, but by exploiting abundant, low-energy prey sources. Its existence highlights the evolutionary principle that apex influence can come from size, specialization, and niche dominance, rather than hunting prowess alone. Through Megachasma applegati, we glimpse a predator that mastered the open ocean not through ferocity, but through efficiency, adaptation, and specialization. Its enormous mouth, subtle teeth, and low-energy cruising made it a midwater giant, reminding us that the prehistoric seas were home to an astonishing diversity of survival strategies, some lethal, some patient, and some, like this one, quietly dominant. Paratodus benedani, the pelagic phantom. In the vast open oceans of the Miocene and Pliocene, Paratodus benedani glided with a ghostly presence, earning its title as the pelagic phantom. Rare in the fossil record, this shark reached lengths of 6 to 8 meters and had a slender, torpedo-like body adapted for long-distance cruising. Unlike coastal predators, Paratodus hunted in the midwater column, preying on large fish, smaller sharks, and possibly marine mammals. Its rarity and elusive lifestyle make it one of the least understood yet most enigmatic apex predators of prehistoric oceans. Unlike ambush specialists, Paratodus relied on endurance and strategy. Fossil evidence suggests a highly streamlined body, capable of sustained swimming over vast distances without tiring. Its tail and fins indicate a design optimized for efficient propulsion, while vertebral flexibility allowed it to perform rapid directional changes to intercept fast-swimming prey. This combination of stamina and agility made it a formidable hunter in the open ocean, capable of exploiting prey inaccessible to slower, heavier predators. The teeth of Paratodus benedeni are narrow, pointed, and slightly curved, designed for piercing and gripping rather than crushing. Fossilized jaw specimens reveal repeated replacement and slight variation in tooth curvature, reflecting evolutionary adaptation to a diet of agile midwater prey. Unlike the broad, serrated teeth of Megalodon or Hemipristis, these teeth were specialized for efficiency in capturing swift, slippery animals, emphasizing precision over brute force. Sensory adaptations amplified its hunting capabilities. Large, forward-facing eyes provided binocular vision to judge distance and speed accurately in open water, while electroreceptors detected faint electrical signals from prey at considerable range. Its lateral line system likely allowed it to sense vibrations across the water column, enabling the shark to anticipate the movements of prey schools or detect approaching competitors. In combination, these adaptations turned Paratodus into a precise and relentless pelagic hunter. Paratodus benedeni likely shaped midwater food webs in subtle but significant ways. By preying on both small and large fish, as well as juvenile sharks, it influenced behavior, distribution, and evolution of multiple species. Its predatory strategy forced schools to adopt evasive maneuvers and likely drove niche specialization in other midwater predators. Despite its elusive nature, its presence created a ripple effect, shaping ecosystems far beyond direct predation. Flexibility defined Paratodus's dominance. Fossil distribution suggests it could inhabit both temperate and tropical midwater zones, tracking prey populations over vast distances. Its slender, muscular body allowed bursts of speed for short chases while maintaining energy efficiency over long cruising periods. This combination of endurance, agility, and adaptability ensured survival in a highly competitive and dynamic oceanic environment. Predatory behavior was characterized by stealth, timing, and efficiency. Likely patrolling vast stretches of open ocean, Paratodus would identify prey from a distance, then strike with a rapid, precise lunge. Fossil evidence suggests repeated strikes on individual prey, emphasizing strategy and skill over chaotic aggression. Its approach contrasts sharply with coastal predators, highlighting the diverse evolutionary solutions sharks developed to dominate different marine niches. Paratodus benedeni demonstrates that apex predation does not rely solely on size or aggression. Its slender form, pointed teeth, and sensory sophistication reveal a predator refined for endurance and precision. By exploiting midwater habitats, it coexisted with larger coastal predators while maintaining apex influence in its own ecological niche, illustrating the adaptive versatility of prehistoric sharks. Through Paratodus benedeni, we glimpse the mastery of open ocean hunting in an era dominated by giants. Its body, teeth, and senses were perfectly tuned to midwater predation, showing that even rare and elusive species could shape entire ecosystems. The pelagic phantom exemplifies how evolution crafted predators not only to survive, but to dominate quietly, efficiently, and with lethal precision. Heterodontus vincenti, the prehistoric horn shark. In the rocky reef environments of the Miocene, Heterodontus vincenti carved out a unique niche as a small but formidable predator. Unlike the giant pelagic hunters, this horn shark measured barely 2 meters in length, relying on specialized adaptations rather than size. Its blunt, molar-like teeth allowed it to crush hard-shelled prey such as mollusks, crustaceans, and sea urchins, a feeding strategy perfectly suited to complex reef ecosystems where agility and precision mattered more than brute force. Unlike open ocean predators, Heterodontus vincenti thrived in environments full of obstacles, coral outcrops, rocky crevices, and tidal pools. Its stocky, muscular body enabled careful maneuvering through tight spaces, while the small dorsal spines provided defense against larger predators. Vertebral evidence suggests slow, deliberate movements optimized for stealth and control, allowing it to ambush prey hiding in the nooks and crannies of reefs. The teeth of Heterodontus vincenti reveal evolutionary specialization. Anterior teeth were pointed for grasping, while posterior teeth were flattened for crushing, a combination that allowed the shark to process a wide range of hard-bodied prey efficiently. Fossilized teeth show wear consistent with repetitive crushing, illustrating how the species adapted to a diet unavailable to larger predators. This dentition underscores the evolutionary advantage of dietary specialization within a competitive ecosystem. Sensory adaptations were finely tuned to a reef environment. Electroreceptors along its snout detected small electrical signals from concealed prey, while the lateral line system picked up subtle water vibrations. Eyes positioned for both forward and lateral vision allowed the shark to detect movement from multiple angles, critical in three-dimensional reef structures. These adaptations ensured Heterodontus vincenti could hunt successfully in a labyrinthine habitat where stealth and sensory awareness were essential. Heterodontus vincenti played a vital role in maintaining reef health. By feeding on mollusks and echinoderms, it helped control populations that could otherwise overgraze algae or disrupt reef balance. Its predation also influenced prey behavior, driving species to adopt hiding strategies or seasonal migrations, creating cascading effects within the reef ecosystem. Fossil evidence suggests it coexisted with larger predators while avoiding direct competition, carving out a niche uniquely its own. Flexibility defined its hunting and survival strategy. Fossils indicate it could occupy both shallow tidal pools and deeper reef slopes, adjusting foraging behavior based on prey availability. Its compact, muscular body allowed quick bursts of movement to capture prey, while energy-efficient locomotion ensured survival in resource-variable environments. This combination of adaptability, defense, and specialized feeding guaranteed a stable ecological role over millions of years. Predatory behavior relied on patience and tactical efficiency. Likely stalking prey from crevices, Heterodontus vincenti could strike with multiple crushing bites, ensuring capture without excessive exertion. Fossilized jaw wear patterns indicate repeated targeting of hard-shelled prey, demonstrating deliberate and efficient feeding behavior. Unlike fast-chasing predators, this shark excelled through strategy, endurance, and morphological specialization. Heterodontus vincenti highlights how small predators thrive alongside giants. Its dentition, sensory systems, and body design allowed it to exploit niche food resources and maintain a long-standing presence in reef ecosystems. By specializing in prey unavailable to larger sharks, it illustrates how diversification in hunting strategy fosters ecological balance and evolutionary success. Through Heterodontus vincenti, we glimpse a predator that mastered the art of reef predation. Its specialized teeth, agile body, and precise sensory awareness made it a small but highly effective hunter. In the Miocene reefs, it exemplified how adaptation, niche specialization, and tactical efficiency can define success, proving that apex influence comes in many forms not only through size, but through ingenuity, precision, and ecological mastery. Notorhynchus sepidianus, the prehistoric seven-gill shark. In the cold, temperate waters of the Miocene, Notorhynchus sepidianus, an ancestor of the modern seven-gill shark, prowled coastal shelves and estuaries with stealth and relentless efficiency. Measuring up to 5 meters in length, it combined a stocky, muscular body with 7 distinctive gill slits, a rare feature among lamniform sharks, which allowed it to respire efficiently during slow cruising and sudden bursts of predation. Its serrated, broad teeth were designed for cutting through large prey, from fish to marine mammals, showcasing a predator optimized for versatility and power. Unlike pelagic hunters, Notorhynchus thrived in structured, near-shore environments. Fossil evidence suggests it navigated rocky reefs, kelp forests, and estuarine channels capable of both ambush and pursuit predation. Its body morphology, with a thick caudal peduncle and powerful tail, enabled rapid acceleration despite its bulk, allowing sudden strikes that would incapacitate prey in confined, complex habitats. The teeth of Notorhynchus sepidianus were evolutionary tools of lethal precision. Upper teeth were broad and serrated for slicing, while lower teeth were narrower for gripping, forming a dual system for subduing prey efficiently. Fossil bite marks reveal repeated strikes on fish and smaller sharks, suggesting calculated hunting rather than opportunistic feeding. Unlike the broad, crushing teeth of Megalodon, these teeth emphasized versatility, enabling Notorhynchus to target a variety of prey within structurally complex habitats. Sensory adaptations enhanced its dominance. Electroreceptors along the snout detected minute electrical signals, enabling it to locate prey hidden beneath rocks or sand. The lateral line system provided spatial awareness across turbulent near-shore waters, while forward-facing eyes offered depth perception for precise ambush strikes. Together, these adaptations allowed Notorhynchus to exploit prey in environments that would challenge other predators, reinforcing its position as an apex hunter. Notorhynchus sepidianus shaped the dynamics of nearshore ecosystems. Its predation influenced schooling patterns of fish, movement of marine mammals, and competition among smaller sharks. Fossil evidence indicates that repeated attacks were common, highlighting its sustained impact on prey populations. By dominating structured habitats, it created ecological pressure that reverberated through multiple trophic levels, illustrating the influence of a mid-sized apex predator. Flexibility defined its hunting strategy. Fossil evidence suggests it could alternate between ambush and active pursuit, depending on prey type and habitat complexity. Its muscular body allowed sudden lunges in narrow channels, while slow cruising ensured energy-efficient patrolling of feeding grounds. This adaptability enabled it to exploit resources unavailable to less versatile predators, ensuring ecological success across diverse nearshore environments. Predatory behavior combined patience, strategy, and brute efficiency. Likely stalking prey with deliberate, slow movements, Notorhynchus could unleash rapid strikes with repeated, serrated bites. Fossilized jaw wear patterns show consistent targeting of similar prey types, emphasizing deliberate and efficient hunting methods rather than chaotic aggression. Its hunting style exemplifies evolutionary adaptation to habitat complexity and prey availability. Notorhynchus cepedianus illustrates the survival of a versatile predator lineage. Its combination of 7 gill slits, serrated teeth, and muscular body demonstrates how specialization in ambush and pursuit could coexist, providing dominance without relying solely on size. By thriving in structured, temperate waters, it shows how mid-sized sharks could maintain apex influence through adaptability and ecological mastery. Through Notorhynchus cepedianus, we witness a predator honed for versatility and precision. Its serrated teeth, muscular body, and sensory acuity made it a formidable hunter of nearshore and estuarine environments. In the Miocene seas, it exemplified how evolutionary success can arise from flexibility, adaptability, and mastery of complex habitats, proving that dominance in prehistoric oceans required more than sheer size alone. Carchahinus obscurus, the prehistoric dusky shark. In the warm, offshore waters of the Miocene, Carchahinus obscurus, an ancestor of the modern dusky shark, patrolled the continental shelves with silent persistence. Measuring up to 6 meters, this shark possessed a sleek, torpedo-shaped body built for long-distance cruising and sudden bursts of speed. Fossil evidence reveals a predator capable of targeting large fish and smaller sharks, combining endurance, precision, and stealth in a manner that allowed it to thrive in open yet structured marine environments. Unlike specialized coastal predators, Carchahinus obscurus excelled in mid-shelf and offshore habitats. Its fusiform body minimized drag, while a muscular, crescent-shaped tail enabled rapid acceleration for surprise attacks. Vertebral fossils suggest a flexible spine capable of agile maneuvers, critical for intercepting fast-moving prey in open waters where escape routes were abundant. This combination of speed, flexibility, and endurance gave it an evolutionary edge over slower competitors. The teeth of Carcharinus obscurus were broad, slightly serrated, and recurved, optimized for gripping and slicing. Fossilized bite marks on fish, turtles, and other sharks suggest repeated strikes and precise feeding strategies. Unlike Megalodon's crushing dentition, the dusky shark's teeth reflect versatility and efficiency, allowing it to capture a wide range of prey without the need for overwhelming size or brute force. These adaptations made it a highly effective mid-level apex predator in offshore ecosystems. Sensory systems amplified its predatory efficiency. Large eyes facilitated depth perception essential for high-speed chases, while electroreceptors along the snout detected faint electrical signals from distant prey. The lateral line system provided spatial awareness and detection of vibrations, enabling the shark to anticipate prey movements even in low visibility. Together, these features allowed Carchahinus obscurus to hunt effectively in offshore waters where prey was scattered and evasive. Carchahinus obscurus shaped prey distribution and behavior across continental shelf environments. Its predation influenced schooling patterns of fish, altered movements of smaller sharks, and impacted the behaviors of mid-sized marine vertebrates. Fossil evidence indicates repeated, targeted attacks, underscoring its role as a consistent apex presence within its ecological niche. Its hunting strategy helped maintain balance within the offshore food web, revealing the influence of mid to large predators beyond sheer size. Flexibility defined its hunting behavior. Fossil distribution indicates it could patrol both shallow and deeper offshore zones, adjusting strategies depending on prey availability. The combination of energy-efficient cruising and rapid, agile strikes allowed it to exploit a variety of prey types across different habitats. This versatility ensured survival even in the face of competition from other apex predators, highlighting the adaptive benefits of a balanced, generalized predatory strategy. Predatory strategy emphasized patience, efficiency, and timing. Likely cruising slowly along the shelf, it could strike quickly, delivering repeated bites to secure prey. Fossilized teeth and jaw wear patterns indicate a predator that applied calculated effort to hunting, conserving energy while maximizing prey capture. Its approach contrasts with ambush or brute force strategies, demonstrating the evolutionary advantage of precision and endurance in offshore habitats. Carcharhinus obscurus illustrates how lamniform sharks adapted to mid-shelf and offshore niches. Its streamlined body, serrated teeth, and sensory sophistication reveal a predator finely tuned for long-range hunting and ecological versatility. By thriving alongside larger coastal and pelagic predators, it maintained apex influence through adaptability, endurance, and skill rather than sheer size, providing a glimpse into the complex dynamics of prehistoric oceans. Through Carcharhinus obscurus, we observe a predator that dominated the Miocene continental shelves, with a combination of precision, versatility, and endurance. Its teeth, body, and sensory capabilities created a shark capable of sustained hunting, influencing prey behavior and shaping offshore ecosystems. In doing so, it exemplifies how survival and dominance in prehistoric seas required intelligence, adaptability, and mastery of habitat-specific strategies. Alopias grandis, the giant thresher shark. In the expansive Miocene oceans, Alopias grandis, the giant thresher shark, cut through the water with astonishing grace. Measuring over 7 meters, its most striking feature was an extraordinarily long, whip-like tail, nearly half the length of its body, evolved to stun and incapacitate prey. Unlike other large predators that relied on teeth alone, Alopias grandis combined precision, speed, and unique anatomical specialization to dominate open waters with efficiency and ingenuity. Unlike ambush hunters, this shark relied on its tail as a tool for hunting. Fossil evidence and analogies to modern thresher sharks suggest rapid, powerful slaps could strike schooling fish, disorienting them for capture. Its elongated body and streamlined shape allowed sustained swimming, enabling it to track schools across thousands of kilometers. Vertebral flexibility ensured it could execute whip-like tail strikes with precision while maintaining stability in the water column. The teeth of Alopias grandis were small, pointed, and recurved, insufficient for crushing large prey, but perfect for gripping stunned fish. Fossilized jaws show tightly spaced teeth, ideal for capturing small to medium-sized schooling prey after immobilization by the tail. Unlike Megalodon's slicing dentition, these teeth reflect a predator that combined mechanical innovation with targeted feeding strategy, maximizing hunting efficiency without relying on brute force. Sensory adaptations amplified hunting success. Electroreceptors detected faint electrical signals emitted by fish, while a sensitive lateral line allowed detection of schooling patterns and subtle water disturbances. Forward-facing eyes provided depth perception for precise strikes, while spatial awareness ensured it could position itself optimally to maximize tail efficiency. Together, these adaptations allowed Alopias grandis to coordinate complex predatory maneuvers in open, unstructured, pelagic environments. Alopias grandis played a key role in shaping schooling fish populations. By selectively incapacitating individuals, it influenced schooling behavior, forcing tighter formations or sudden dispersals. Fossil evidence and comparative studies suggest its predatory impact extended across multiple species, indirectly affecting midwater predators that relied on the same prey. Its presence illustrates how a predator can exert influence beyond direct consumption, shaping the structure and behavior of entire ecological communities. Flexibility defined its hunting strategy. Fossil distribution indicates Alopius grandis occupied temperate and tropical waters, following prey migrations over long distances. Its body allowed bursts of speed for short, precise attacks while maintaining energy-efficient cruising. This combination of endurance, mechanical innovation, and adaptability enabled it to thrive in open ocean ecosystems with variable prey density. Predatory behavior relied on a mix of endurance, precision, and timing. Likely stalking schools of fish slowly, Alopius grandis could strike with sudden tail slaps, then quickly capture stunned individuals using its recurved teeth. Fossilized jaw wear patterns indicate repeated use for gripping, suggesting that efficiency and technique were as critical as anatomical specialization in securing prey. Unlike predators relying on sheer force, it relied on strategy and coordination. Alopius grandis illustrates the potential of biomechanical innovation in apex predation. Its elongated tail, streamlined body, and specialized teeth reflect an evolutionary path, emphasizing technique over brute force. By exploiting pelagic niches inaccessible to slower, heavier predators, it exemplifies how evolutionary adaptation can create apex dominance through precision, flexibility, and functional specialization rather than sheer size. Through Alopius grandis, we witness a predator that turned anatomy into a hunting tool. Its whip-like tail, precise teeth, and coordinated predatory strategy enabled dominance over midwater prey in vast Miocene oceans. It exemplifies how ingenuity, specialization, and ecological mastery defined prehistoric sharks, reminding us that apex influence could arise from creativity as much as from raw power. Heptranchias perlo, the ancient seven-gilled hunter. In the shadowy depths of Miocene oceans, Heptranchias perlo, an ancestor of the modern seven-gill shark, prowled with quiet precision. Measuring up to 3 meters in length, this shark combined 7 gill slits with a slender, flexible body, making it an efficient mid-water predator. Its pointed, recurved teeth suggest specialization in gripping soft-bodied prey such as squid, small fish, and benthic invertebrates. Unlike its more aggressive contemporaries, Heptranchias relied on stealth, patience, and precise strikes in dimly lit habitats where agility outweighed brute strength. Unlike fast-chasing sharks, Heptranchias perlo thrived in low-light, mid-water, and benthic zones. Fossilized vertebrae indicate a highly flexible spine capable of sudden twists, enabling ambush attacks from above or below. Its body design allowed it to navigate rugged underwater terrain such as canyon slopes and rocky outcrops, while conserving energy during slow patrols in search of prey. This combination of endurance, flexibility, and tactical stealth made it a subtle yet effective hunter. The teeth of Heptranchias perlo were slender, sharp, and slightly recurved, forming multiple rows in the upper and lower jaws. Fossil evidence shows these teeth were perfect for piercing soft-bodied prey, ensuring they could be securely captured and swallowed whole. Unlike the crushing dentition of benthic horn sharks or the slicing teeth of coastal lamniforms, these recurved teeth exemplify specialization for agile, elusive prey. Their repeated replacement over a lifetime underscores the evolutionary importance of maintaining hunting efficiency. Sensory adaptations were critical for predation in dimly lit habitats. Large eyes provided enhanced low-light vision, while electroreceptors detected the faint electrical impulses of hidden prey. The lateral line system detected water movements, allowing the shark to anticipate approaching prey or predators. Together, these adaptations enabled heptranchias to navigate and hunt with precision in environments where visibility and maneuvering were challenging, reinforcing its role as a midwater specialist. Heptranchius perlo played a subtle but important role. By preying on soft-bodied midwater organisms, it regulated populations of squid and small fish, influencing the structure of midwater food webs. Fossil evidence suggests repeated attacks on prey indicate strategic, sustained hunting rather than opportunistic feeding. Its presence in benthic and midwater habitats likely influenced the behavior and evolution of other predators and prey, showing that even smaller sharks could exert significant ecological influence. Flexibility defined its hunting and survival strategy. Fossil distribution shows it could operate at varying depths, adapting hunting strategies depending on prey availability and environmental conditions. Its slender, muscular body allowed bursts of rapid movement for capture, followed by energy-efficient cruising for long-distance patrols. This adaptability ensured survival in habitats where resources were scattered and competitors were numerous. Predatory strategy emphasized stealth, efficiency, and timing. Likely approaching prey slowly and deliberately, Heptranchius could deliver precise, repeated strikes with its recurved teeth. Fossilized wear patterns on teeth suggest repeated targeting of preferred prey, highlighting strategy and precision over brute force. Its hunting style contrasts sharply with open ocean lamniform predators, demonstrating the diversity of evolutionary solutions among sharks. Heptranchius perlo illustrates how specialization can secure survival in competitive environments. Its combination of 7 gill slits, recurved teeth, and flexible body enabled a unique predatory niche, coexisting with larger sharks while avoiding direct competition. By mastering midwater and benthic zones, it demonstrates the power of adaptation and strategy in shaping ecological dominance, even without massive size or brute force predation. Through Heptranchius perlo, we glimpse a predator that mastered stealth, precision, and adaptability. Its slender body, recurved teeth, and specialized senses allowed it to dominate midwater and benthic habitats, influencing prey behavior and maintaining ecological balance. In the Miocene seas, it exemplified how evolutionary success could emerge from strategy, specialization, and mastery of complex environments, proving that not all apex influence is wielded through size or aggression alone.